All right, here we go for part 3. Example 6. Determine the slope of the tangent at x equals 1 to the curve, blah, blah, blah. Then make sure your answer is consistent with a rough sketch of the function. Yeah, we want to do a rough sketch of this polynomial function. It's awful, but we're gonna do that eventually. Slope of the tangent, that means take the derivative, right? So we're going to take the derivative, and how do we sort of think of this? We can think of this in 3 pieces, right? There's 1, 2 pieces, there's the third piece. And so I'm going to use the extended product rule and think of, well, I'll take the derivative of the first thing. Derivative of the first thing, just minus 3, no inside part. Write down the second parts. All right, I just wrote them down. Plus, this is how the product rule goes. Write down the first thing. I guess I could have made that minus 3x there. And now, derivative of the second thing. Derivative of the second thing is uh, power of a function rule. So the 5 comes down. Write down the inside thing, the exponent, and now the derivative of the inside thing is just 1, but I'm going to write it in there just to make sure that I didn't forget to take the derivative of the inside thing. And then I write down the last part. Plus derivative of the first, derivative of the second. Now I'm going to write down the first 2 things. And then write down the first 2 things. Derivative of the last thing. I wonder if I can do this. I'm going to, oops. Just because I'm running out of room here. Some smartboard magic for you. Okay, plus, wrote down the first 2 things, derivative of the second thing, or derivative of the third thing. The 3 comes down, right, goes down to squared, and then I got to write down the inside thing. It doesn't change. And then the derivative of the inside thing, right, the derivative is actually something. 2x plus 3, the 4 disappears. Okay, great. And now I actually have to find the slope at x equals 1. But notice, that sounds bad, but it's not bad at all, because at x equals 1, do you see what happens? That's 0. This is 0. This is 0. And it's all multiplied, right? So this 0 will wipe this out. This 0 will wipe this out. This 0 will wipe that out. So at x equals 1, y prime equals 0. And so there is a horizontal tangent, right? The slope is 0. What does that mean? Well, it's probably a min or a max. And that's why they wanted to get us to draw a sketch of this. Now this sketch is actually not much fun, but what we'll do is we'll talk about it real quick. Our function skills would have zeros at x equals 0. X equals 5 is actually a fifth root. A fifth root is like a slide, a super slide almost, because x to the exponent, x to the exponent 1, or x equals 1 is a 5/5 degree root. Super slide. Here, this is weird because this is a quadratic, right? This is a quadratic that actually can be factored into x plus 4 and x minus 1. So in fact, this is a cube, and this is a cube. So this is a degree, x equals minus 4 is degree 4. And x equals 1 is actually, there's another 3 there, so there's 8 altogether, right? Degree 3, so 8 copies of x minus 1 altogether as far as our root is, our sketch is concerned. So I got 0, I've got 1, 1, and it's actually an 8th root. It's going to be a bounce now. And where was the other one? -4. So -4 is out here. I know it starts low and ends high, or starts low. And how many? What's the degree altogether? We got 1 there, 8 there is 9, 10, 11, 12. So it's degree 12 altogether. Crazy. So it starts low and ends low. At 4, it's a slide. 4, it's a slide. 0, it's a slash. And then what happens at 1? Well, since it's a degree 8 altogether, it's a bounce. And notice, that's what we wanted. At x equals 1, it was indeed a bounce. Slope equals 0. We knew it all along. Crazy. Okay, last one. This is, I like this example. This is like a business example, and I know it's getting late and you're getting tired of writing notes, but this is a great example. An ISP, Internet Service Provider, uses the models B at whatever and C equals whatever, where B is the number of business subscribers. So this is the number of business subscribers, and C is the number of connections for each business. So this is like internet connections. T is the time in months. And so what is it saying? It's saying, what does N represent? Well, if this is the number of businesses and this is the number of connections for each business subscriber, then N, the product, is just the total number of connections needed. At time t. Time t months. Notice that for this one, we could, by all means, we could multiply this out. It's not so bad, but the reason why this is such a good example is because it shows that the product rule makes a little bit of sense as far as the derivative of one write down the other one, and I want to show you that. So n at t is just bt times ct, the number of connections. And so the derivative is then derivative of the first, write down the second, plus write down the first one, derivative of the second one. And these functions are pretty easy. So b prime at t, I'm going to write down as 50. C prime at t is a nasty number. 2 times that, 0.000 8 t, right? And the t goes down to 1. So there's my derivatives that I'm going to use. And so now, if I write this, and this is 50 times and this is the derivative function. And I know I could have expanded this, but I want to show you something. This is cool. And that number's okay. So what this shows, by the way, is this is the change in the number of connections that the internet service provider needs. And it's based not just in the change in businesses and the change, it's the interplay between, okay, maybe the number of businesses is changing. It's going up by 50 businesses a month, right? 50 businesses a month. But each of those businesses requires that many connections. Or also the businesses each business is requiring more connections that has the rate of change is this, and that depends on the number of businesses, right? So overall, the number of connections here, this number of connections is, well, the number of businesses is changing for each connection, and The number of connections is changing, and it's the interplay in between the two functions that kind of makes sense. So, and this is a nice illustration of that. Um, if we just want to find out what this means, it's not that interesting, I suppose. But n prime at 12, all I would have to do is take out the t and put in the 12 and calculate that. Uh, calculator work, calculator work. Not very interesting. I'm not going to copy all this down. You can work that out, and I got it to be about 486.4. So what does this mean? This means after 12 months, because T is 12, after 12 months, the company, it needs 486 more connections per month. The number of connections required is increasing by 486.4 connections. That doesn't make any sense, but that's okay. Uh, connections per month. And I like that example. That's a nice business example. Okay, long video. Tomorrow or next day is the quotient rule. Things sort of pick up a little bit. Hopefully we were getting the idea and of how to take derivatives, especially of these polynomial functions, and it's going well, I hope. Good luck with your homework.